Hello and welcome to part 6 of the Demystifying Fiber Optics series by the Fiber Wizards. In this last section, we'll provide a high-level overview of the most common methods used for field testing fiber optic systems. The first thing that we want to do before testing any fibers is to inspect the connectors. To ensure that the light signals generated by transmitters actually make it into the fibers, we got to make sure that the connectors are very clean and that are free of dirt, scratches, or any other irregularities that could limit the transmission of light into the fiber, or even block it. As the core diameters of fibers are small enough to be measured in microns, any airborne contaminants such as dust particles could very easily impact the signal. To ensure the consistency of evaluation and reporting, it is recommended to use inspection probes that have automated software. Another common method for verifying fibers is by visual inspection with a tool called Visual Fold Locator, or VFL, which is basically nothing but a small handheld laser that emits red light. With the VFL, we can inject visible light into fibers to verify continuity or identify them while working with multiple fibers or ports in connecting hardware. Also, the red light is powerful enough so that if there are any excessive bands, pinching, or fractures causing attenuation or reflectance issues near the VFL, there will be a glow from the leak light marking the location of the issue. The next method that we will discuss is called insertion loss testing. This is perhaps the most important test of all, as it determines whether the optical link will allow the light signal from the transmitter to reach the receiver with enough power for the link to work. Insertion loss test is performed with a light source and a power meter. First, the test equipment components are referenced and set to 0 decibels. Then, light is injected on one side of the link, and at the opposite end the power is measured. If the reference value is captured in the equipment at the beginning of the process, the equipment itself will compare the before and after values and will calculate the insertion loss according to the resulting difference. To conclude, we will look at a full-length optical performance test that is done with an equipment that uses time domain reflectometry. Basically, this test consists of sending out a light signal using this equipment commonly known as an OTDR. As the signal travels along its path, the light is reflected from elements in the fiber, creating backscattering that returns to the equipment. Once the equipment processes the backscattering fluctuations, it creates graphical representations that tell you the distance of the span, the calculated total loss, and the resultant optical performance after the light travels through any connector, splices, accessories, or any other performance impacting irregularities along the fiber path. Here we will demonstrate how the OTDR works. First, a launch reel or pulse suppressor is placed at the laser output of the equipment. Another fiber reel is also used at the opposite end of the path to let us know where the light passes through the last connector of the link. Then, the launch reel is connected to the port of the fiber to be tested, the equipment parameters configured, and the equipment set to begin the test. As you can see, the device shows us information of the link along its path, including connection points, splices, and possible failures, giving us an end-to-end view of the optical link. Well, fellows, though we hope to have achieved to demystify fiber optics for you, we encourage you to continue exploring fiber technology and feeding your curiosity. For now, we'll leave you, but don't stop connecting with us either through our website, social media channels, email, or by any means. Thanks everyone. Many blessings, and we'll see you soon.